All right, we're going to get into polynomial functions in this section. So all polynomials can be written in this form where the coefficients of the x are all real numbers, and then the degree must be a whole number. So degree's got to be a whole number, right? And then that nth is the degree. The largest value is your degree of that polynomial. Polynomials are unique. They're very smooth. Their graphs are unique, I should say. They're smooth and continuous. So that might be a polynomial, or a quadratic's a polynomial. Again, smooth and continuous is the name of the game with a polynomial. So let's take a look and just determine, first of all, is this a polynomial? Let's look at the first one. I'm going to put it in order. Negative 2x to the third. I'm going to put that 1/3 x squared and then plus a 3x. And if you take a look at this, I'd say, well, first of all, are all the degrees whole numbers? Yes, they are. That's an x to the 1, by the way. So they are whole numbers, and all the leading coefficients are real numbers. So this, yes, is a polynomial. And so the degree is 3. This is a third degree polynomial. In other words, it's a cubic. Third degree, it's cubic. That's the name for a third degree. Let's look at this next one here. F of x equals the square root of x. In other words, x to the 1/2 minus 5. And hopefully you see that to the 1/2 power and you think to yourself, no, this is not a polynomial because it's not a whole number up there for the degree. Let's look at this next one here. F of x equals, let me write it as 5x to the negative 2 is the same thing as 5 over x squared. That is also not a whole number, so this is not a polynomial. This next one here, f of x equals 6. And this one actually is a polynomial. Let me rewrite this another way. 6x to the 0. I know that this is your constant on the end, so this is a 0th degree polynomial. So yes, polynomial. They don't write that x to the 0 because remember, anything to the 0 is 1. So this is just like 6 times 1. They don't write that x to the 0. But it is a polynomial, and you should know it is a degree 0 polynomial. In other words, it's a constant. It's a constant. Y equals 6. It's just that horizontal line. Y equals 6, right? It is a polynomial. Nice and smooth and continuous, but that's what a constant looks like. This next one actually is, it's not in your standard form, so you could go ahead and put it in that form if you wanted to recognize that, oh yeah, this is a polynomial. Yes, it's a polynomial. And notice it is a degree 2. It is a second degree polynomial, which we know from the last section means it's a quadratic. Well, polynomials have at most n minus 1 turning points. Okay, so for example, this one, x squared minus x to the 5th, which really should be written as negative x to the 5th plus x squared, could have up to n minus 1 turning points. And turning points meaning, here, let me show you a graph. This graph has 1 right there, 2, 3 turning points. That graph has 3 turning points. So that's where you have local minimums and maximums. Turning points happen at peaks or valleys like bottom of the hill, top of the hill, or bottom of the valley, right? Peaks or valleys. So local minimums or maximums are turning points. So a 5th degree polynomial, this y equals negative x to the 5th plus x squared, could have at most up to, it's a 5th degree, 5 minus 1 or 4 turning points. Again, I don't know what this looks like, but it's not going to have won't have more than 1, 2, 3, 4 turning points. Maybe that's what that thing looks like. Who knows? But it's not going to have more than 4 is the point. So the degree minus 1. So which of these could be a third a degree 3. Well, if it's a degree 3, like let's say it's a 2x to the third plus 7x minus 1, degree 3, it'll have at most 3 minus 1, 2 turning points. At most 2 turning points if it's a degree 3. So this couldn't be it. The first one could not be it because I have 1, 2, 3, 4. So that's not it. The next one, I'm looking at this next one. This can't be it because it's not continuous. It's not continuous. Remember, it's got to be continuous and smooth, right? This next one can't be it either because it's got a sharp edge. It's not smooth. Okay, so that's out. That's out. It's not smooth. No jagged edges. The third one's got to be it. And notice it has 1, 2 turning points. Again, it could have less, but it's not going to have more than 2 turning points if it's truly going to be a third degree polynomial. Well, this next one says form a third degree polynomial. So third degree polynomial whose zeros are, so the x-intercepts, here's my x-intercepts, -2, 0, and 2. And then it also passes through the point -1, 6. So let's go ahead and have a third degree. So it won't. So in other words, at most 2 turning points, right? And we're going to go ahead and form a degree 3 polynomial that might do that. You might look at, maybe it goes like this and crosses through and it goes like that, right? Notice it has 2 turning points, right? There's a look at a possible graph of a degree 3 polynomial that passes through that point. But we're going to go ahead and create one. Okay, create one. So let me erase this, get a little room here. Let's kind of give you the visual of that. If you know what a 0 is, like let's say, for example, x squared minus 4. Here's x squared minus 4, right? And notice it has a 0 here at 2 and a 0 here at -2. Well, if you know the zeros, then you could say x minus the 0 must be a factor. So there's x minus the -2 and x minus the +2. In other words, x plus 2 and x minus 2 must be factors of it. So, well, we already knew it was x squared minus 4. We could have already factored that into x plus 2, x minus 2, right? But what I'm saying is you can go backwards from your zeros back to the actual function if you're given enough information, okay? So this one has the zeros -2, 0, and 2. So I don't know what the number is in front. I'm going to call it a, but then I'm going to go x minus the first 0. If -2 is a 0, then x minus -2 is a factor. If x equals 0 if 0 is the next one, then x minus 0 is a factor. If 2 is the next 0, then x minus 2 is a factor. So here's what we have so far. X plus 2 times x minus 2. I'm going to go ahead and write the x right after the a, and then the x plus 2 and the x minus 2. I'm going to write it like that, okay? Now, I also need to use this information. I have the point -1, 6. So after I clean this up, what I'm going to do is, let me go ahead and multiply x plus 2, x minus 2. That's x squared minus 4. Let me distribute that. So we have x cubed minus 4x, okay? So now I'm going to plug in the -1, 6 and solve for a. So x is -1, y is 6. Divide by 3, so it looks like a is 2. So there we have it. This is our form, and we know a is 2. So this ends up being 2x cubed minus 8x. That's the equation, and I should write it up here. 2x cubed minus 8x. That's the equation of a degree 3 polynomial that goes through -2, 0, and 2, and it has the point -1, 6. And of course, you could take a look at your Desmos, and you should see when you plug in this function, 2x cubed minus 8x, maybe. Notice there's our x-intercepts right there, and right there. And then it also goes through that point right there, -1, 6. I'm going to have to show you with the, here we go. Whoops. Right there. If I plug in -1, I'll get 6. I don't need the rest of these points. I'm just trying to show you the point right there, -1, 6 as well. Okay. Before I move on to the next one, I want to point something out. This last one had 3 zeros, and it was a third degree. So whatever your degree is, you should have that many zeros or x-intercepts, right? If it's a degree 3, you'll have 3 zeros. If it's a degree 4, you have 4 zeros, and so on. So this next one's asking me to say, hey, find a degree 3 polynomial, and it has a 0 of -3 and 1. Well, they only gave us 2 zeros, so one of these must be a repeated 0. So degree 3 must have 3 zeros. So let's make -3 is with multiplicity 2. In other words, it hits it twice. In other words, the graph, I don't know what the graph would look like, but what it means is it'll just touch there instead of cross through. It'll touch there. So I have my zeros, I'm going to say are -3 and another -3 and then a 1. So when I create this function, x minus the first 0, x minus the second 0, again I got 2 of those, and x minus 1. So I have x plus 3 squared and then x minus 1. Now, it also said, but it has a coefficient of 1. So they're telling us that this is a 1. So this is actually our function. And of course, we could expand that out if we wanted to into, we'd have x plus 3, x plus 3, x minus 1. So we'd have x squared plus 6x plus 9 times x minus 1. Take the x through. Take the -1 through. You got x cubed. You got 6x squared minus x squared plus 5x squared, 9x minus 6x, 3x minus 9, right? And that would be the other standard form of this one. So if you have even multiplicity, your graph will cross. It'll touch it, and if you have odd multiplicity, it'll cross. So for example, let's say we have this function here. Let me write it this way. I have 2, and see how I have xxx? There's 3 of these x's. So that's one of my zeros. X equals 0. Right, if I'm finding the x-intercepts, I let y be 0. I take each of these factors. Say it equals 0. So 0 with multiplicity 3. So since it's odd multiplicity, so at 0, odd, it'll cross through. So it'll cross through like that, or it'll cross through decreasing like that. And then the second one, So I would set this factor equal to 0, x minus 1 equals 0, but there's two of them. X equals 1 with multiplicity 2. X equals 1 with multiplicity 2, so it'll just touch it right there, either from the bottom or from the top, because there's an even amount of those zeros. This next one, again, if I was letting y be 0, I would take each of these factors and set them equals 0. So the next 0 is negative 2 with multiplicity 4. So it also touches, right? And I should have said this one touches, the first one crossed. So now we're at negative 2, and there's an even amount of those, so it'll touch it either from the bottom or from the top. Okay? If you take a look at that graph, you'll see this thing will come from here. It'll kind of touch here. I'll have to come back down. It'll cross through, and then it'll touch. It'll be kind of something like that. Again, I didn't draw very well, obviously, so I didn't plot any points there. But that's kind of the feel that you would have for this, okay? Based on just on the zeros. Now the end behavior is also very important. The end behavior tells us what it does at the extremities. So when n is even, remember this is your form, x to the n plus blah, blah, blah. I like to think y equals x squared. That's your classic. It goes up to the left and up to the right, right? So any even degree with a leading coefficient that's positive, so the leading coefficient's also positive. So if n is even and the leading coefficient's positive, it's going to go up to the left and up to the right. The graph will. Okay, so for example, let's say I had 7x to the 4th plus, I don't care what the rest is. It's even and it's positive. So eventually it'll do that. Again, I don't know what's going on in the middle, and I don't care right now because we're just talking about end behavior right now. Okay. Now, if you have even degree but a negative in front, so think like negative x squared, that'll go down to the left, down to the right. So n is even, but the leading coefficient is negative. Down to the left, down to the right. Now, if you are odd situation, I like to think about x cubed. If I'm odd, right, remember x cubed looks like this, right? But I'm generalizing this. If I'm the n is odd, x to the 3rd, but the leading coefficient is positive, it'll go down to the left, up to the right, just like x cubed. But if it's odd, but the leading coefficient is negative, it'll flip that around the x-axis. So it'll go up to the left, down to the right. Okay, so that's kind of how I remember end behavior. So let's go ahead and we'll go ahead and construct a polynomial function from this graph here. Based on that information. Notice it goes down to the left, up to the right. So I know it's n is odd, the degree is odd, and I know the leading coefficient must be positive. Right, so that's this one right there that I circled, right? Odd and leading coefficient positive. Now, the second thing I note after I think about the end behavior there, that just kind of gives me some information, is I'm going to go ahead and list my zeros. So I have a 0 of negative 4, I have a 0 at negative 1, and I have a 0 at 2. And they cross through. That means I only have an odd amount of each one of those. So I'm just going to assume I just have one of each, since the least amount to be odd would be 1 here. And then what I'm going to do is I'm going to say, well, this function is, I don't know what the leading coefficient is, I just know it's positive. And then I'm going to construct it from the 0. So x minus the first 0, x minus the next 0, x minus the third 0. And now all we got to do from that is use a point on the graph. Usually the easiest point to use if you have a nice integer for the y-intercept is I would use that point, 0, -2. So now use 0, -2 to solve for a. So y is -2, x is 0, and let's go ahead and solve for a. So it looks like -2 equals a times -8. Divide both sides by -8. A ends up being a fourth. So we have step 3 here. So we got to this point, and now we know a. A is a fourth. And there's our function. And by the way, if we multiplied this all through, this would end up being 1/4 x to the third plus, I don't know what the rest of it is if I was to multiply it all through. But notice the degree is odd and the leading coefficient is positive. Okay, and you would get that exact graph. Thanks so much for watching. See you guys next time.